Hey guys, today we're going to be looking at radioactive decay. And now the standard for this says that we're going to compare the types of radioactive decay in terms of the particles and the energy that the radioactive decay generates. Now, what this basically means, and what I'm going to be expecting from you, is I want you to be able to differentiate between the various forms of radioactive decay given the particles and or the energy that is released during the process. So the first thing that we need to understand is what radioactive decay really is. So we have a definition, and we're going to go through it and break it down piece by piece. So radioactive decay is the spontaneous transformation. Basically, this means that it's the instant change of one radioisotope into one or more different isotopes. So a radioisotope is basically just a radioactive element, atom, material. And what this is going to do is it's going to change into another element, atom, material. So if you look at the periodic table, it's going to go from one element to another element. Now this is also going to be accompanied by a decrease in radioactivity. So after this process is complete, the final product is going to be less radioactive than the original product. Now a little more vocabulary for us is that the original material is called the parent material. And now what is produced is going to go by what we'll say is the daughter products. Alright guys, so there are three types of decay that we are going to look at. The first is alpha decay. Alpha decay produces an alpha particle, which is a helium nucleus. It's denoted by this symbol here, and being a helium nucleus, it has a mass number of 4. Remember, the mass number is the number of protons plus the number of neutrons. It has an atomic number of 2, meaning that it has 2 protons. The second type of decay that we're going to look at is beta decay. It produces a beta particle, which is an electron. It's denoted by this symbol here, and as stated, it's an electron. Now the electron does not have a mass number, but it does have an atomic number. Now the atomic number is -1. The reason for it being negative is because it's an electron, and electrons have negative charge. The final decay that we're going to look at is gamma decay. Gamma decay produces a gamma particle, which is a high energy photon. A high energy photon is basically just an electromagnetic wave. Now the gamma particle is denoted by this symbol here. It comes from the nucleus. It has no charge and no measurable mass, but it does have energy. Alright guys, so the first type of decay that we're going to look at is alpha decay. Now on the left hand side of the arrow, we have our parent material. In this case, it is an iridium atom, which has a mass number of 226 and an atomic number of 88. The daughter product of this reaction is a radon molecule. And we also have our alpha particle being released. Now when working out radioactive problems, it's important that we retain our mass number, which means that the mass number needs to be the same on the right-hand side and the left-hand side of the equation. And we also need to keep our charges the same on the left-hand and right-hand side. So what we would do is we would add the helium molecule to the radon molecule. So for the mass number, we would go 4 plus 22. Now this gives us 226, which is the same as this side. Since we have the mass number accounted for, we now need to look at the atomic numbers on each side. For the radium molecule, we have an atomic number of 88. On the daughter side, the radon molecule has an atomic number of 86 and the alpha particle a number of 2. Now we want to add the atomic number of the alpha particle and the atomic number of the radon particle. If we go 2 plus 86, this gives us 88. Thus, we have 88 on the daughter side and 88 on the parental side. One thing I want to point out is that the alpha particle is leaving this decay process with a lot of energy, and this is the reason why radioactive decay is not good for us. The second type of decay that we're going to look at is beta decay. This is depicted in the image displayed in front of you. For this decay process, we start with a lithium molecule as our parental material and a beryllium atom as our daughter material. And an electron is released in the process. The first thing we want to do is make sure that our mass numbers are the same on each side. So first we'll start with the parental material. We see that lithium has a mass number of 8. Now moving to the daughter side, we see that beryllium has a mass number of 8 and the electron has a mass number of 0. Now 8 plus 0 equals 8, so these are balanced out. Now we're going to take a look at the atomic number. On the lithium side, the atomic number is 3. On the daughter side, beryllium has an atomic number of 4, while the electron has an atomic number of -1. If we go 4 plus -1, we get 3. So we have 3 on the lithium side and 3 on the daughter side. They're equal, and it's balanced. So what we're going to look at now is what's happening on the periodic table, which may help you better grasp what is occurring in decay. So with the alpha decay, we started with a radium molecule. We lost 2 protons in the alpha particle that was released because it was a helium nucleus. So if we go down 2 protons on the periodic table, we go from radium to francium to radon. So during alpha decay, you're going to drop 2 spaces in the periodic table. You're going to go from 88 to 86 in our case. Now during beta decay, a little different process is happening. We're losing an electron. So we're losing a negative charge, but we're gaining a positive charge. Now if we look at our example, we started with lithium and we went to beryllium. So we started with 3 protons. We lost an electron, but we gained positive charge. And we went to 4 protons, beryllium. This is what will happen during beta decay. You'll go up a spot in the periodic table. In this way you can visualize what's occurring on the periodic table as what's occurring in the decay process, which may help you better grasp the concept. So we've made it to our final decay process. So in front of you is gamma decay. So if we look at the gamma decay, and we look at the left-hand side of the equation, at the parental material side, we see that there's a plutonium atom. Now, if we go to the right-hand side, there's still a plutonium atom. There has been no changes in the atoms themselves, but what's occurred is a gamma ray has been released. The gamma ray, as discussed earlier in the video, has no mass, has no charge. The gamma ray is energy, it's radiation. This is what occurs in gamma radiation. A gamma ray is released, but there is no change in the atoms themselves. So what's important is that you recognize when gamma radiation is occurring and what's going on in the process. Alright guys, so that's our 3 types of radioactivity. And when you come to class, we will do some problems and expand on this knowledge.